Hello everyone, this video is going to cover the concept of angular momentum. Just like for translational motion, we have linear momentum, P equals m times v. By substituting in the rotational versions of those variables, we get an expression for angular momentum, L equals I omega. We can apply this same idea to the other relationships we know dealing with angular momentum. So remember that we had the impulse momentum theorem, which states that F net times delta t equals the change in momentum, and so we would have the rotational analog of that statement, net torque times delta t equals delta L. And finally, remember from the impulse momentum theorem, we saw that if the net force is 0, then delta P equals 0, and so the linear momentum of the system is conserved. Similarly, we have the law of conservation of angular momentum, if the net torque on the system is 0, then the angular momentum of the system is conserved. One way in which that idea is often applied is in what's called the figure skater problem. So if you have a spinning figure skater, you may have noticed if you've ever watched figure skating, the rate at which the skater spins changes depending on the position of the skater's body. So let's say that a figure skater with her arms extended has rotational inertia or a moment of inertia I, so we'll call that I naught, and spins at an angular speed omega naught, and she then brings her arms close to her body, and I want to know first, does her rotational inertia increase or decrease? And then I'll give you a factor by which it changes, and we'll figure out the factor by which the angular speed changes. So let's say that I changes by a factor of 2. You first want to think about whether I increases or decreases. So a figure skater who started with her arms extended and then brings her arms in closer to her body, she has changed the configuration of her body so that her mass is concentrated closer to the rotation axis. So I is going to decrease. Same mass, but now on average that mass is closer to the rotation axis. It's easier to change the way that she is rotating. And if we want to find then the skater's new angular speed, there's no torque on her body, no net torque acting on her body during this process, so the angular momentum of the system, in this case the skater, is conserved. So L initial equals L final. Or I naught omega naught equals I final omega final. But we know that I has changed by a factor of 2, and we discussed earlier that we know it must have decreased. So I final equals I naught divided by 2. And plugging that in, we have I naught omega naught equals I naught over 2 times omega final. The I naughts cancel, and so omega final would equal 2 omega naught. And again, from the idea of conservation of angular momentum, it makes sense that the skater's angular speed has increased. We know that the moment of inertia has decreased. The angular speed must increase to compensate for that, to keep the product I omega the same. And if you watch a video of a figure skater spinning, you'll notice that the figure skater's angular speed, the rate at which he or she rotates, does change accordingly. If the body is brought closer to the rotation axis, the rotation rate, the angular speed, increases. If instead the arms and legs are brought farther from the rotation axis, the angular speed decreases, the rate of rotation is less. We can also think about angular momentum of a single particle as a little bit of an odd idea. Even if we're thinking about a single particle that itself does not have any spatial extent and does not rotate, we can still think of it having rotation relative to some point in space. So let's say that we have a particle of mass m moving with some velocity v. Here, much like when we've talked about with with rotational inertia, where we have to define the axis around which the object is rotating, and that choice of axis changes the value of I. Similarly here, this single particle will have different angular momenta relative to different points. And so we are going to define a point O, which the particle has angular momentum with respect to. And we're going to define an r vector in much the same way as we did for torque. R is going to point from that point O to the current location of the particle. And in this situation, the angular momentum, sometimes still referred to as capital L, sometimes it's a script lowercase l instead for a single particle. Really doesn't matter which one you use. They both stand for the same thing. But here, L would equal mvr sine phi, where phi, similar to before, is the angle between r and v. And so on this diagram, this angle would be phi. A very common way of thinking about this is to think about grouping r and sine phi together. We can see from this diagram a reason why we might do that is that r sine phi is this distance here, which is the perpendicular distance between the point O and the line of the velocity. So the particle is going to move, in this case, horizontally straight across, but that value r sine phi is staying the same throughout, no matter where it is. And so here, if the object moves with constant velocity, it will have a constant angular momentum. When it's far away from the object is far away from point O, the r vector will be very long, but phi will be very small, sine phi will be small, in such a way that the product r sine phi is staying the same. Here, the idea of rotation, again, we're thinking about a single particle, so it is not itself rotating. What we're thinking about is the rotation of the r vector. So, as the particle moves, the r vector, in addition to changing length, is also going to rotate. For instance, if we imagine the particle moving to the right side of O rather than the left, r will have rotated from quadrant 2 into quadrant 1. And so the rotation here is the rotation of the r vector, but is still angular momentum in the same sense as for a solid object that is rotating. We would treat it in exactly the same way. We could have a collision between a single particle and an extended object in which both linear and angular momenta are conserved, and this angular momentum of a single particle would be on exactly the same footing conceptually as the angular momentum of a solid object rotating.